Hey guys, this is Casey and my friends Tyler and Olivia, and we're UNC students who love CRISPR. We're interested to know, do our fellow students love CRISPR just as much as we do? Well, let's find out. We conducted a short survey and distributed it throughout campus. With a few different questions about genome editing, we found that most UNC students know the basics of CRISPR, but we noticed some things that could be clarified more, so let's break it down. CRISPR stands for clustered, regularly interspaced short palindromic repeats, and it's found in bacteria. It's used as a defense mechanism against viruses and is a vital survival tool for the oldest war on the planet. But how does it work? When a virus attacks a bacteria, it inserts its own DNA into the cell, hijacking the host cell's DNA reproductive systems to produce more viral DNA, or simply more viruses. In bacteria with the CRISPR system, the viral DNA is integrated into a CRISPR locus of spacers via the Cas1 and Cas2 enzymes. These spacers are acquired from viral phages that invade and are meant to match their DNA to a high degree, but can be variable, with the sequence best matching the virus being known as a protospacer. These spacer sequences are then converted into cRNA, which is just a precursor RNA to gRNA formation, with each cRNA containing one unique spacer sequence. This cRNA is then combined with tracer RNA, transactivating CRISPR RNA. Don't worry about this guy too much, he's just kind of there, to form a guide RNA that will be the leader for our mission. The gRNA will then go find the big bad Cas9, a nuclease enzyme that cuts DNA. But where does Cas9 cut? This is PAM. That stands for protospacer adjacent motif, which helps our big CRISPR-Cas9 system locate its target. The gRNA binds to PAM, which is usually an NGG sequence, and Cas9 will cut right behind PAM. Like our well-known PAM spray, this sequence doesn't allow anything else to stick. And just in case you were worried, the CRISPR arrays in the bacterial DNA do not have PAMs, so CRISPR doesn't accidentally destroy the good DNA. So now what? Once Cas9 cuts the viral DNA out, the DNA is repaired either by non-homologous end joining or homologous recombination. Essentially, the CRISPR defense mechanism works kind of like spell check in that it cuts out and attempts to fix mistakes. Big shout out to our queens, Drs. Doudna and Charpentier, who discovered how this whole process works. So what does this mean for us? Well, CRISPR was originally discovered in cheese factories and explored to see if it could help protect the product from contamination. Next time you eat Greek yogurt, remember to thank CRISPR if you don't get sick. But recently, CRISPR has expanded into a whole new world of applications. Cancer medications, hypoallergenic cats, being a cool professor, glowfish. Okay, perhaps we were kidding about the professor part, but fixing color blindness, reviving the woolly mammoths, getting rid of malaria, HIV treatments, vaccines, buff horses, designer babies, and food with natural pesticides, and the list continues on. It seems like the possibilities are virtually endless, but are they? Well, we always fall back on the law, but it's not there yet. It's kind of like the Wild West out here, folks. Well, can we patent it at least? Yes and no. So what's the sitch? Well, Doudna and Charpentier did discover this process and want to patent the technology, but so does Zhang. The Zhang lab was the first to apply the technology to mammalian cells for medical application, so it's kind of hard to say who deserves the credit on this one. And let's certainly not forget ethics. In our study, we found that UNC students still have doubts about using CRISPR technology, especially when it comes to themselves. Although we don't know everything about CRISPR, the technology has been thoroughly studied and we're learning more about it every day. Things like designer babies have also been of great concern, especially when we consider the inevitable commercialization of this technology beyond simple genetic testing and treatment. These babies will be able to pass on their genes and affect the whole gene pool over time, so it's important to lay out what can and cannot be edited, as well as push for inclusion and non-discrimination of peoples when it comes to edited versus unedited people. Once this door opens, it cannot be closed again. So tell me, how do you feel about CRISPR now that you know how it works and a few of its applications? For Tyler, Olivia, and I, we side with CRISPR, but only with the proper regulations.